Okay, so we are going to talk about one more thing from section 2.3. So it's not actually true that this is all about 2.5. So the one more thing we need to cover is called the squeeze theorem. So suppose we have an interval containing x equals a, so that's going to be the point that our limit is going to approach. Maybe I should mention that the squeeze theorem is another way that we can evaluate limits. So we have an interval containing the point we want to approach, and for each x, so for each x in the interval, f of x is less than or equal to g of x is less than or equal to h of x. So we have g of x sandwiched between these two functions, f and h. And if we have that the limit as x goes to a of f of x is equal to L, and the limit as x goes to a of h of x is equal to L, then that forces the limit as x goes to a, actually I'll put this down here, so then the limit as x goes to a of that function that was in between them, g of x, that also has to be equal to L. So the picture here would be, so say we have a function h and another function f, and here's our point A, right? So here's f, here's h, and then g is in the middle. So you can see that the reason why it's called the squeeze theorem is because it's being squeezed down to that point, so it makes that function also approach L as x approaches a. Okay, so sometimes this is also called the sandwich theorem, just because, well, same idea that it's being sandwiched between those two functions. Okay, so let's do some examples. So in the first one, we are given that this function g is actually sandwiched between two functions. So we're just told that right off the bat, right? And so all we need to do is look at the limit. So we want the limit as x goes to 1. So we want to just compute the limits of the functions on either side, and if they're the same, then we can use the squeeze theorem to say that the limit as x goes to 1 of g of x is equal to whatever that may be. So for this one, this is a polynomial technically, and so we just plug in 1 and we get 2. And if we take the limit of the other function, we have x to the 4th minus x squared plus 2. So that will give us 1 minus 1 plus 2, so also 2. Okay, so by the squeeze theorem, without knowing any other information about the function g, we can say that the limit as x goes to 1 of g of x is equal to 2. Okay? Alright. Now here is another example. It's a little bit more involved. So we are told to use the squeeze theorem for this function, but we aren't given the functions that are going to lie on either side of it. But what is useful about trig functions is that we have this fact. So for sine and cosine, it's always the case that they lie between -1 and 1. Sorry, I should put cosine of x. Right? Okay, now that is almost our function. We just need an x out front. So we can just multiply through by that x. The thing is, we have to be careful because it depends. So when we're dealing with inequalities, whether we're multiplying by a positive number or a negative number, it may change the inequality, right? So if we did have that x was positive or 0, so non-negative, then we would just multiply through by x, knowing that it's not changing the inequalities, right? And so we would get this. On the other hand, if x was less than 0, so if x was a negative number, then what would happen is the inequalities would flip, but we would actually get the same thing. So we get negative x is greater than or equal to x cosine x is greater than or equal to x, like that. Okay? So let me I'm going to rewrite this one as x is equal to cosine x is less than or equal to negative x, and then okay, so together what these two things tell us is that so putting these two together is that negative absolute value of x is less than or equal to x cosine x is less than or equal to absolute value of x. Okay, so let's look at the first, or let's look at the right hand side of this inequality. So if x is greater than or equal to 0, then x cosine x, let me just circle the part I'm focusing on right now, then x cosine x is less than or equal to x. Now, since x is greater than or equal to 0, this is the same as the absolute value of x, right? Because we don't change anything by taking the absolute value of a positive number. In the bottom, so in the second inequality, we have x cosine x is less than or equal to negative x, and that is also equal to absolute value of x, because remember, we're assuming that x is negative. So if x is negative, then we switch the sign by putting a negative in front, and that is equal to the absolute value of x. Okay, so these two together for these two different cases give us that x cosine x is less than or equal to absolute value of x. And then the other inequality is going to be basically just the mirror image of that. So I'm not going to go over that one. However, okay, so we have this inequality, and then we can take the limit as x goes to 0 of each of these sides. So the limit as x goes to 0 of absolute value of x, or so I'll do the first one first. So the negative absolute value of x, this is just equal to 0. So one way of seeing that is to notice that, so the absolute value of x, its graph looks like a V. It looks like that. This is absolute value of x. So negative absolute value of x would just be that flipped over the y-axis, or x-axis, sorry. Okay. So we can see from the graph that it is approaching 0. But also, we don't really have any issues if we just go ahead and plug it in. So long as you don't get 0 in the denominator, a logarithm of a non-positive number, so 0 or a negative number, So those are issues, and then also taking the square root of a negative number. So as long as you don't run into any of those issues, you can basically plug it in, right? Okay, so the same thing goes here. We can say that the limit as x goes to 0 of absolute value of x is equal to 0, right? So what we get is that this function x cosine x is going to be squeezed to be 0, so to approach 0 at that point. So if we wanted to draw a function, I don't know exactly what x cosine x looks like without, using a graphing calculator or something to figure that out, but I know that it will have to pass through this point. So let's say it looks something like this. So see that because of the shape of these two functions and them converging towards 0, the limit as x goes to 0 of x cosine x has to also be 0. So by the squeeze theorem, And so if you do use the squeeze theorem, I would like for you to write this part out. So make it very clear that you know that you're using the squeeze theorem to evaluate the limit. So x cosine x is equal to 0. And that's our answer.